Okay, in this video what we're going to do is we're going to look at an electric dipole. What an electric dipole is you have two charges of opposite signs, so you have a positive charge and a negative charge. And in this case, looking at this dipole, we're going to figure out the electric field at point P right here. Okay, so let's take a look at this problem. So we're going to take the same steps as always. My first step is to find the direction of the E field of each of those charges. So for no good reason, really, I'll label these, call that one 1 and 2. And remember what we do to find the direction of the two of them is pretend that this point P is a positive charge here. And that P here is going to give us the reaction of that. Let's go ahead and do that. So if I look at Q1 right here, it's a positive charge, and this is positive. So the E field at this point would be away. So I'll call that E1 like that. So remember, it can only push in a straight line, and it's going to be going away from that component right there. Now, when I look at this one right here, I see that it's negative, this is positive, this is going to go toward. So the E2 is going to be up that way and toward, just like that. Now, these are the same values, so technically they should be the same length here. So let me just be a little more official. They're also the same distance apart, too. So I'm going to go ahead and do that. That's E2. Okay, well, looking at these, what we're trying to figure out what's the net force like this. So I know a little symmetry about this problem. I know that they're the same distance apart and technically, well, they're the same charge. And if you look, you have a down and an up. What's going to happen is the up's going to cancel the down and these are going to add up. So we're going to probably see something like this. Is that this charge will actually have an E field to net looking something like that. That's what I predict here. So let's see why. So the next step is I'm going to find the strength of the E. So find basically my values for E1, E2, and again, just the strength, no signs for this. When I do this, so E1, aka Q1 or R1 squared. This is 8.99 times 10 to the 9th newtons meter squared over coulomb squared. Q1 is this is in micro, so that's going to add a times 10 to the negative 6 coulombs there for the micro. And then I'm going to divide it by the distance. Now the distance must be in centimeters, so I'm going to go ahead and convert that immediately into 0.07 meters instead. So I'm just going to go ahead and set up the next one. That's how I find E1. E2 is going to be K Q2 over R2 squared. And hopefully not surprisingly that this will be the same exact setup here because they're literally the same numbers. It's going to be 6. I'm ignoring the sign because I'll get direction later. And it's negative 6 microcoulombs, so that's the negative 6, and I ignored the sign. And this is at the same distance. So notice I don't want the 10 here. I want the 7 because that's how far apart they are. So I want the 0.7. So notice that these are essentially the same value. So let's go ahead and calculate these out. 2.99 to the 9th times 6 e to the negative 6 divided by 0.07. We get a large number when we do that. So let's go ahead. So that's 1.10 times 10. So let me count. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So we're doing to this positive 7. And this is newtons per coulomb. And this will actually be the same value. Newtons per coulomb. Just like that. And that's E1. And this will be E2. Okay. So we just found how strong they are. Now we got to analyze their x and y. So we have to analyze each of them in terms of their x and y components. So that's when I usually take them out of the problem, right? So let's start with E1. I'll put this one over here. So E1 looks like this. I'm replicating the direction of it. To make this arrow, I have to go down and to the left. That tells me that this is going to be negative and that's going to be negative. So the hypotenuse is what we just calculated. That was what we did. Our problem is, what is this and this? But notice we don't have an angle here. So we got to figure out what this angle could be. And what we're going to do is use some geometry to figure that out. So that's where this 10 might come in handy. So let's see. So this angle right here is basically the flipped angle of this right here. So if I know this angle, then I'll know our angle over here. So how do we do something like that? So what I'm thinking is, if I split this triangle in half, I can make a new triangle. So I'm going to go ahead and do it. And actually what I'm going to do is do it like this. So just with the geometry, okay, so I split this bottom. This bottom will be the same as this bottom. So that's 5 centimeters. Now, this length I don't know, but I do know the hypotenuse. I do know that this is 7 right here. So I have this and this, which is just enough to find my angle. So I have an adjacent and a hypotenuse. And when you look at SOHCAHTOA, I hope you see that if you have an adjacent and a hypotenuse, that's going to be a cosine. So cosine of adjacent over hypotenuse. If I want to solve for the angle, that's going to be the inverse cos of my adjacent, which is my 5, divided by 7, and that's going to be my angle. So I'm going to go ahead and solve that. 5 divided by 7, I get 44.41 degrees. So that's this angle. And essentially I found that angle right here. That's what this triangle represents, which is the same as that angle up there, because I split this in half and made this a 5 and made that 7. So this is my angle right here, 44.41. It's almost 45, but not. That's really funny. Okay, so now I want to find my x and y. So I'll start off with finding x. My EX1 is going to be my E1 times cosine of the angle. Now the reason why it's cosine, for the same reason I solved it up here, if I want this leg of the triangle, and I have an angle and hypotenuse, that's a cosine. Same idea, if I want this leg of my triangle, I have an angle, a hypotenuse, and this which is opposite, which makes it a sine. So this is going to be E1 sine of the angle. So 1.10 times 10 to the negative 7, positive 7, sorry, positive 7 newtons per coulomb times cosine 44.41 here. And this is going to be 1.10 times 10 to the 7 newtons per coulomb times sine 44.1 here. So let's go ahead and solve these out. 1.10 e to the 7 times cosine 44.41. 7.86 times 10. 1, 2, 3, 4, 5, 6 newtons per coulomb. Let's go ahead and do the next one. Times sine 4.1. And this is 7.6. This is 7.7 times 10 to the 6th newtons per coulomb. I'm just going to double check that. 1, 2, 3, 4, 5, 6. Okay. All right, now that I got the x and y, I look at the signs. Notice this is going left and this is going down. So these are both going to be negative numbers because this one is down and this is left. All right, let's take a look at E2. E2 looks like this. And this is E2. Okay, E2 is going to have an arrow that goes left and up. That's why I can make that arrow. Okay, so now E2, let's take a look. We don't have an angle, so let's see if we can figure it out. If you look at this diagram, we have this angle. According to alternate interior angles, this angle is going to be the same as this angle right here, which is what we have drawn here. So cool, this is the same angle. And to kind of save some work here, you can go ahead and this would be a sine. I'm sorry, this would be a sine, this would be cosine. Notice that this is the same triangle as this. So, cool beans, it means we have the x and y values already. My x here is going to be the x value here, 7.86 times 10 to the 6 newtons per coulomb. And then since this is going left, that will be negative. EY, I'm just going to write actually over here as one arrow. EY is going to be that value, 7.7 times 10 to the 6 newtons per coulomb. But this one is going up, so that will be actually positive because that's up and this is left. Okay, now that we got our x's and y's, we add them up together to get our total. So let's go ahead and do that. Okay, my E1x is negative 7.86 times 10 to the positive 6. I just want to write negative newtons per coulomb. My y is negative 7.7 times 10 to the 6 newtons per coulomb. My x for E2, it's the same number. So essentially we're going to be doubling this. Now this is the same number but positive, which means they are going to cancel. So this is a nice 0 because they cancel. These essentially double. I'm going to go ahead and just do the 6. What I get? 1.57 times 10 to the 1, 2, 3, 6, 7. We're getting bigger. Newtons per coulomb. They're both negative. There. So this has an interesting result because notice that this is 0 and then this is left over right here, which means I don't need to make a triangle because my final answer is all in one direction. It's only in the x. So even better, I can just write this as a statement that the final net force is 1.57 times 10 to the positive 7th newtons per coulomb left. So notice that left means this way, to the opposite way. Or you could write it as negative, but essentially this is it. That's the answer. It's going to be pushed to the left. So, just like I predicted right here, I saw that this up force will cancel that down force in terms of the y, and you're going to be left over with E. So in the end, this will go to the left. And that's our final answer. So we didn't have to make a triangle because final E field in one direction. And that concludes this example.